Welcome back to part 5 on exponential functions. One of the most familiar examples of exponential growth is that of an investment earning continuously compounded interest. Using exponential functions, the following formula is developed. Now, you don't have to necessarily understand how this was derived, but it is a good idea to refresh your memory on future value of an investment. This will allow you to calculate how much money you would have in the bank at some future time t. If you have $10,000 that is invested at 6% annual interest, compounded semi-annually, that means 2 times a year, come up with a model that gives the value of the investment after X years. Well, we know that time is in years, so we'll say t is equal to X. We also want to know how much money you will have at the end of that time. So we'll say A of X is equal to the original principal, the present value of the investment for t years, that's $10,000, times 1 plus the rate. Well, we said it was 6%. We'll put it as a decimal. So 0.06 divided by n. This is the number of times interest is compounded per year. So n equals 2 times per year. And then we'll raise this to the n times time. So it will be 2 times x. Now, if we want to know how much money will be in the account at any given time, we just substitute some number in. Let's say 7 years. We could figure out how much money is in the account after 7 years simply by replacing x with some number. This is what's so nice about a formula. To understand continuously compounding, or compounding every instant, consider an investment of $1 for 1 year at 100% annual interest rate. Let's fill out the following table, rounding your answer to 5 decimal points. First, we're given compounding information. The first compounding is annual. This would mean n equals 1 compound per year. If we had monthly compounds, it would be n equals 12. If we had daily compounds, n would be 365. If we had hourly compounds, we have to get our calculator out. So if we have 365 times 24 hours in a day, that will give us 8,760 compounds per year. And lastly, if you remember the song, minutely, if you have compounds every minute, you'd have 525,600, because you could take what you were given and then multiply it times 60. This would be how many minutes you have. So if we wanted to figure out what the future value would be for each one of these investments based on the number of compounds, notice that as we go through this table, our compounds are going to increase. Let's take n equals 1 and put it in our future value formula. We know that time is 1, so in place of t, we'll put 1. We have an investment of $1, so we'll put 1 out front. And we're investing for 1 year at 100%. So that's 1 over the number of compounds per year. In this case, it was 1. All raised to the n times t, which is 1 times 1. So if I simplify the stuff inside, I'll have 1 times 2 raised to the 1. This is just 1 times 2, so I will get 2. I'm going to continue this process for each n value. $1, 1 plus 1 over the number of compounds 12 raised to the 12 times 1. And I'm going to do this all in one step at the end, but for now I'm going to write out what I'm calculating in the formula. Notice that the 365 is in the denominator, and so are all these compound values. It's also the exponent. So when we are compounding minutely, we would have a of 1 is equal to 1 times the quantity 1 plus 1 over 525,600 all raised to the 525,600 times 1. So now let's find out what each one of these outputs or future values would be. I'm going to use my calculator, and I'm going to enter this in my y equals. So I'll have 1 times the quantity, 1 plus 1 divided by x, close parenthesis, all raised to the x times 1, which I'm not going to put the times 1 in. So click on the window button after you push the second button. And let's have this start at 0. And I'm going to set the independent variable to ask. That way I can calculate each one of the outputs. And now I'll do second table. And my first ask value will be 12, because I already know this one is 2. My first output is going to be 2.613. My second ask value is going to be 365. And my output is 2.7146. Now my ask value is going to be 8,760. And my output is 2.7181. Last one will be the giant number, 525,600. And my output is 2.7183. Now I want you to notice that as we continue to make n larger and larger, we could say as n approaches infinity, a of n approaches e. So we could say the conclusion is that the number of periods per year, as they increase, the future value increases and gets closer to the number e, but will never exceed it. So we use the following formula for continuously compounding stuff. You have a of t equals p times e raised to the r times t. If we wanted to find the future value of $2,000, which is invested for 10 years at 5% annual interest, compounded continuously, we could substitute it into the formula a of t for our future value for continuous compounds. When time is 10, our principal is $2,000. E raised to the r, 5% annual interest rate is r, and we'll write it as a decimal. So e to the 0.05 times t, and we know t to be 10. If we calculate this, we'll get 2,000 e raised to the 0.05 times 10. And the future value in our account will be $3,297 and 44 cents.